At 9:45, stop on 5.
Somerset by DuMont. A library cabinet in mahogany and finish for your home.
WABD, New York.
This man is blowing glass for science. The Johns Hopkins Science Review, presented by the Johns Hopkins University and WAAM in Baltimore. This is the Johns Hopkins University, famed for its contributions to science and the humanities. Here in its many laboratories, Hopkins scientists are constantly probing into the secrets of science, which, when discovered, are translated into benefits to be enjoyed by you, the people of America. Each week, we look over the shoulders of today's scientists and catch a glimpse of their research. On this, our 177th telecast, we learn about blowing glass for science. And here to introduce this week's program is Lynn Poole of the Johns Hopkins University.
Good evening, ladies and gentlemen, and welcome to another Johns Hopkins Science Review. We here on the Johns Hopkins Science Review are very happy tonight, and we'd like to share our pleasure with you. Because the Johns Hopkins Science Review is being seen in Montreal and Toronto, Canada. We're very proud that this program is the first American program to be broadcast each week in Toronto and Montreal. And we want to pay tribute to the stations in those two cities, and to tell you how glad we are to be cooperating with you and working with you. And to all of you people in Montreal and Canada that are viewing these programs, we want to send you our heartfelt happiness that we are there. And we hope that you're going to enjoy our programs. We're going to do everything we can to make them worthwhile, entertaining, and interesting to you. Because we feel very close to you, that minuscule border is between our two countries is a border that hardly exists because of the friendship that has existed between our two countries for so long. And we here at Johns Hopkins are particularly glad because for so long we have had such close association with McGill University and with the University of Toronto and many of the other schools in those areas. Now, whether you are at McGill University or the University of Toronto or at Johns Hopkins University, there is one thing that I'm sure we all realize, and that is behind the scientific research that is carried on in these institutions, there are many people that help, and one of those persons is the glassblower. Now, to show you what I mean, I have a little piece of glass in my hand here. It's a glass spring. It goes back and forth, just like this. Now, a master glassblower blew this. Why did he blow it? Because it was important to the scientists. It was important to the scientists that there be just so many rings here, that these rings be in exact size, because the scientific research that the professor wanted to do could not be carried out unless these were exact. And these things cannot be purchased because they must be made to exact specification of the scientist. Now, rather than just talking about it, let me show you a piece of apparatus that we have here. Look over here for just a moment. This piece of apparatus was blown at the Johns Hopkins University and is being used at this time in the chemistry department for a specific piece of research that's being carried out. And I'd like to call your attention to this bulb up here in the corner. And then I'd like you to follow down with me here and see these pieces of glass and the little stopcocks that are on there. Now, those could never be manufactured and in exactly that way. Because, as I said before, the scientist needs a specific number of them and needs them placed in a specific manner. And then, finally, over here. Notice this little part to the apparatus. This, we might say, is the real business end of it, because this is filled with a liquid, and the chemist wants to know a certain particular answer from this. Now, the man that blew and prepared this entire apparatus is a master glassblower, Mr. John Lehman, who works in the laboratories at the Johns Hopkins University, and I'd like you to meet him and see the type of work that he's doing. Mr. Lehman, I judge that you are preparing the very first part of this piece of apparatus that I've just shown.
I'm starting to make this here glass pliable, Mr. Poole, so I can blow that ball up.
Well, now, we've had the pleasure of having you as our guest before, last year, and I think even the year before. And you told us a bit about the methods that you use. But one thing you did tell us last year was why you keep that moving in the fire all the time.
Well, the reason why I keep tying this, Mr. Poole, is if I was to stop tying it, why, it would get lopsided and get all out of shape. So by turning it or revolving, why, it keeps it in the position that I want it to. Now this here is, I'll blow this ball, it'll be about 3 inches in diameter when I get done with it.
I must say that is a very perfect bulb, Mr. Lehman.
Well, now you pull this end off here so I can get it into the center, so I can splice that other piece of tubing on. It goes down in that apparatus there that holds their liquid or their specimen that they use.
Mr. Lehman, that glass really turns to liquid in there. How hot is the fire that you use?
These fires right now, Mr. Poole, are about 1,800 or 2,000 degrees. It has to be hot enough so it'll melt this glass so it'll run like water. Now, the reason why it takes me so long to blow is I'm getting it up to the right size.
And by burning it and blowing it, you have opened a hole in the other end of that little ball you have there.
That's right. And then we spliced this piece of 8mm tubing on to bring it down to that size on what we call that shaker machine over there.
Mr. Lehman, when you put the glass tubing on that bulb, why do you blow it again?
Well, the heat of these here fires shrinks that glass, so then you have to blow it in order to get up to its size.
And that size, of course, must be absolute and exact.
Yes, unless the professor or the student, he wants a taper to it so the liquid will run down easier for him.
When you have it to the satisfactory size and have that tubing put on, why do you again put it into the fire?
To sort of equalize the heating in there, because if you just hold it in one spot like that, you create a strain in there. And by running it back and forth in the fire like that, it puts an even temperature on the glass and cools down evenly so that it leaves no strain in there. Now that's on there. Now I come out here about 6 to 8 inches and make a bend so it'll fit the right distance that they want it. And you dasn't get this glass too hot to make a bend, and you dasn't blow it too quick.
I believe you told me you called that an arm bend.
Yes, a right angle bend.
I wonder if I might have it just a moment here, because I'd like our viewers to see it. The glass ball here, the tubing there with the arm bend, the right angle bend. Now, as we see this, let's again take a look at this piece of apparatus and see where it fits. As you can see, the ball is in that portion, the very top, and the arm runs up and around and comes down again. Now, Mr. Lehman, of course, would put another arm bend right here to bring it down. Now, we have a second part of this apparatus that Mr. Lehman is going to prepare for us, the pieces of glass with these stopcocks in them. Let's watch him as he does that.
Well, these two stopcocks, Mr. Poole, they have to be a certain distance apart in order to fit in that apparatus.
What makes the snapping and crackling in the fire?
That's the heat of that, and then there's a slight leak back here where that gas is escaping. And by me bringing this hot glass back here, it catches on fire and sputters.
Well, I'm glad you mentioned the leak, Mr. Lehman. I wasn't going to mention it, but as I stand right here, I can really smell it.
Now that's the two stopcocks joined together. Now they have to have another outlet on the side there. So you come over here to this torch that I have here, and you blow a small hole in there in order to get that other stopcock on there. We call this, if it wasn't a stopcock, it would be just a sidearm. And you dasn't get that too hot, or else the whole piece of glass gets hot, and then when you go to put that sidearm on, it gets out of shape. And you just have to blow this hole just to the right size.
Now you're heating just one side of that piece of glass tubing.
That's right, yes. So then you just get these two hot, sticking together. These have to be vacuum tight, so you got to make sure that there's no pinholes or anything in here.
No pinholes in the joint that you're making.
Right.
I noticed that you can turn that for several seconds after you take it out of the fire. It still stays that hot.
Yes, it does. Now, if you'll hold it up there, you won't get burnt.
If I hold it anyplace else, I will. How about over here?
It's a little warm.
A little warm, but not too hot, and I would like you to see this close up because this is part of the center section of this piece of apparatus that Mr. Lehman made some time ago. We notice how he put together the one tubing in here, fitting it very carefully and fitting it to an exact measurement, too, in order that these various stopcocks would be in the right position so that when they are turned, they will allow just the right amount of chemical or gas or whatever it is go right through. Now, let's go back and look again at our apparatus here and see where this fits. Here we can see the various pieces of glass tubing that Mr. Lehman put together and how these stopcocks were put on it. This, I think you might call on this piece of apparatus the control center of the whole thing. Now, there's one more piece that I'd like Mr. Lehman to blow for us, and I see he's working on it right here. You started with one whole tube and you're pulling it apart.
Yes.
Isn't that what you just did there, Mr. Lehman, called pulling a point?
Yes, Mr. Poole, that's one of the most important parts of this business, is pulling that point.
Why is it so important?
Well, it makes it easy to control the glass, and it acts as a handle, which I'm putting on here now. Now, when I put that standard taper on there, that's got to come out right in the center of where this handle is. And it also makes it easier for me to control it.
Now, that handle that you just pulled off there will have nothing to do with the piece of apparatus when you're finished.
No, sir, I'm going to pull that off, pull this end off, and that'll be the one rounded end. And then when I get that standard taper on there, well, that'll be the other. Then I'll use that to pull this other end off with and round it off. You'll notice I'll bring this over here, and that hole has got to come out right in the center of where that handle is. And then again, you'll notice the important part of me turning this piece of glass.
You have to keep that entire section heated all over the section to exactly the same degree.
That's right, Mr. Poole.
Now, this is the section that you're going to put on it. Why are you putting that paper on it?
I'm putting that piece of paper in there, Mr. Poole. When you get this close to the heat, if I didn't have that piece of paper in there, it would freeze on me from the heat. So just by putting that little piece of tissue paper in there, why, that stops that.
It's a strange expression that freezes from the heat. Now, the two openings, the one from the object in your left hand and the one in your right, must meet and be exactly the same size,
That's
mustn't
right,
they?
yes.
Now you have them about the same size, blowing them so that they really fit tightly together.
That's right. And then I just pull this off.
So that you will then go on and complete the thing. And while Mr. Lehman is completing it, I would like to take a look at the piece of apparatus and see again the thing that he's working on at this very moment. You can see how the two pieces have been put together, and I would like to point out to you the little locks on the side where the springs come down. Now, Mr. Lehman will go ahead and put those little locks on from the outside in order that the two pieces will be held together. Many of you may have wondered just exactly what this apparatus is and how it's used. So as Mr. Lehman continues to finish it, let's look at it more closely and ask Mrs. Marjorie Melville of the chemistry department at Johns Hopkins if she'll tell us what this is and how it works.
This apparatus that Mr. Lehman has made is called a hydrogenation apparatus. A material is placed in the apparatus, a material which will absorb hydrogen, and the amount of hydrogen that it will absorb is measured. The material that we're using now is an organic compound, sorbic acid. The material is placed in this container that you see here. The container is attached to the rest of the apparatus by two springs and these four glass hooks. that Mr. Poole pointed out before. The device that's used for shaking the container containing the compound which will absorb hydrogen consists simply of two strings. One string is attached to a motor. The other string is connected to an ordinary screen door spring that you see here. Now, before we fill the apparatus with hydrogen, we want to remove most of the air that's present in the glass tubing. In order to do that, we attach a vacuum pump at this point here. The vacuum pump then, when it's turned on and these stopcocks are open, the vacuum pump will remove most of the air that's present in the glass tubing. And after that, we can close off this stopcock and allow hydrogen to enter the system. The hydrogen comes from this tank here. The hydrogen is let into the system through this valve. It then comes through this stopcock and through this second stopcock and then up into the glass tubing, through the ball, around the bend, down the long glass spring, and into the container which contains the solution of the material that will absorb hydrogen. Now, in order to tell how much hydrogen is absorbed by the material, there are two columns of mercury here, one on your right and one on the left. As the material in the container absorbs hydrogen, the height of the two columns of mercury will change. As the material absorbs hydrogen, the level on the right, which is now here, will rise, and the level of the mercury on the left will drop. So knowing the difference in levels of the two columns of mercury, we can find out how much hydrogen was absorbed by the material. Now, to start the apparatus, we start the motor and start the shaking device, and you can see the liquid shaking back and forth in the container, and then it will start to absorb hydrogen. A practical application of this apparatus is the absorption of hydrogen by vegetable oils to form solid vegetable shortenings that are used in cakes, pies, and other cooking purposes.
Mrs. Melville has given us a very practical example of the use of a piece of apparatus like this, because I doubt that many of us knew that vegetable shortenings must absorb hydrogen, and of course the scientists must know how much it will absorb before it's getting the right consistency. Now, the piece of apparatus that you've seen here is being used in the Hopkins laboratories for more basic, more fundamental pieces of research than working on shortening. But nevertheless, it's a very important part of the research that's being carried on in the chemistry laboratory, and the glass blower has had a great part in it. And I'd like you to see something else here that a glass blower had a part in. If you looked at it in this shape, perhaps you wouldn't recognize what it is. But if I turn it around like this, I'm sure that most of you would recognize what it is. If I hold it up closer here, you can see that it's a cathode ray tube. And as you know, the cathode ray tube is a part of your television set. And it's on this screen here, in this cathode ray tube, that you are viewing this program right now. Something similar to this in your own sets at home. Well, now, what did the glass blower have to do with it? Well, Dr. Alan B. DuMont is the man who developed and brought this cathode ray tube to the full flowering of its development so that it could be used for television. And he had a glass blower that worked with him on this cathode ray tube. And I have a photograph here that was taken in 1931 in the basement of Dr. DuMont's home in New Jersey. And here you see Mr. Stanley Coach. Mr. Stanley Coach was a glass blower that helped Dr. DuMont in his work. And as Mr. Lehman blew glass here tonight, so Mr. Coach blew glass and blew the first cathode ray tube that was invented and developed by Dr. DuMont. Now we have another photograph. Here you see Mr. Stanley Coach with Dr. DuMont over there standing behind him. And if you look very carefully, in the left-hand corner, you will see a whole series of these cathode ray tubes that were blown by Mr. Coach in the early days of television for the development of the television sets that we have today. And one more photograph I'd like to show you is Dr. DuMont himself here holding a later cathode ray tube. Now, of course, the one that he's holding in his hand was not blown by Mr. Coach, the glass blower. Later, other developments came along, and these cathode ray tubes were made in a different manner. But nevertheless, the glass blower is the man that helped, the man who blew the first cathode ray tubes in order that you and I may enjoy television. So you see, the glass blower is a very important man in scientific research. And when you hear of some great discovery, some new development in the field of science, well, think about the glass blower, because he was probably a man that was there when a great deal of the work was going on. He was there when television was a youngster. Now, of course, television is one of the most amazing and exciting things in our contemporary world, this 20th century in which we live. But there are other things that are amazing and exciting, too. And then amazing things when people talk about flying into space, going out into space, being catapulted out in a rocket, careening through space, and arriving someday on the moon. Now, I'm perfectly sure that this is going to happen, and I have a feeling that it's going to happen in my lifetime and in your lifetime. And during the next 3 weeks, the Johns Hopkins Science Review is going to bring you the facts about space travel. So we hope that you'll be with us for 3 weeks when we tell you how man will conquer space.
Scientists in the field of astronautics tell us that rockets can be constructed which will carry men out into space. How will this be done? When will it be done? How can man live in space? What sort of rocket will be built? And how will it be propelled on its trip to the moon? The facts are more exciting than fiction. And during the next 3 weeks, we will demonstrate the facts of space travel, how spaceships will be built to carry human beings to the moon. For these programs, we are bringing to Baltimore the leading astronautical engineers, Dr. Heinz Haber from California, Dr. Martin Summerfield from Princeton, Dr. Werner von Braun from Alabama. These men will join Hopkins astrophysicists to bring you the exciting story of how man will conquer space. The Johns Hopkins Science Review is produced by Lynn Poole. Directed by Paul Kane. Associate producers, Robert Fenwick and Warren Whiteman. The Associate Director is Ed Serro. Art direction by Barry Mansfield. Your narrator has been Joel Chaseman. Parts of this program have been mechanically reproduced. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the DuMont Television Network. Next, program.